let's look at solving sample test number 3. All right. Number 1, the pressure on a round stool with radius 1 meter. Elephant stands on it, on the whole top with his feet. So basically we're just saying that the area that we're going to use is the top of the stool. It has radius 1 meter. So the area is going to be pi r squared. Pi times 1 squared. So pi square meters. All right. And so we want the pressure. We have several equations relating to pressure, but the kind of defining one is force per unit area, or force per area. And so we've got the weight of the elephant is going to be a force, right? The mass times gravity. So force is going to be mg. And so we've got 1,000 kilograms times g, 9.81 meters per second squared, and divided by a, which is just pi. So we can get p, calculator, if we can see that. Might work. All right, so just plugging in 1,000 kilograms times 9.81 meters per second squared divided by pi, and we get 3.1226. Pressure is in pascals. If we got everything else in the right units, and so we'll just say that is 3.12 pascals. Whoop, 10 to the negative 3. I'm sorry, 10 to the positive 3. Didn't see that. 10 to the third. So it's 3.12 kilopascals. All right. Part B. Buoyant force of the ball of radius 0.2 meters when submerged in water. Water density given. Okay, so buoyant force. So we're going to assume it's submerged, means it's all the way under. And so buoyant force, remember, is rho g v, where this is the density of water, and this is the volume of water displaced. Okay, so if something is partway submerged, it wouldn't be the total volume of the thing, but if it's only partially, if it's totally submerged, then it's going to be equal to the volume of the thing. And so in this case, it's totally submerged, so V of water is going to be V of the ball. We'll assume the ball is a sphere. Volume of a sphere, 4/3 pi r cubed. All right, so we've got r, and so we got density of water, we got gravity, so we can get the buoyant force. So B equals density of water, 1,000 kilograms per cubic meter, times gravity, 9.81 meter per second squared, and then times the volume, 4/3 pi r is 0.2 meters squared. Oh. So we plug that in, 1,000 minus 9.81 is 4 times pi times 0.2 squared, and don't forget to divide by 3 for the 4/3. Alrighty, so we've got 1.643. So we'll call it 10 to the third. This is force, so it's newtons. Everything else was in the right units, so we should be good. And so, yeah, so what do we got? 3 sig figs, 1640 newtons. Okay. Number C, letter C. Average angular acceleration. So find the average angular acceleration of a car that goes from rest to 40 meters per second around a corner of radius 50 meters and in 7 seconds. So we've got a circle, part of a circle. Radius equals 15 meters, excuse me. And the car is going to start at rest and end up going 40 meters per second. Okay, so when we got meters per second, that's velocity. But we're talking about angular acceleration, which is alpha. So alpha, and we're asked for average. So the average angular acceleration is going to be the change in angular velocity over the change in time. So omega minus omega naught over, we're given that was a total, so maybe t final, t minus t initial, or however you want to look at it. It's just going to be 7 seconds there. All right, so we need omegas. We do have the equations for relating linear things to angular things, that v equals omega r. And so that's gonna, we can get omega then is v over r. And so when v is 0, omega is also 0. When v is 40, omega will be 40 meters per second over r, just 50 meters. So omega will be 0.8 radians per second. All right, so plug that in. 0.8 minus 0, the initial one was 0, over the total change in time, which was 7 seconds. These are radians per second. And so we get alpha is 0.8 divided by 7. 1143 10 to the negative 3 radians per second squared. All right, so alpha equals 0.114 radians per second squared. I'm sorry, it's 114.3 times 10 to the negative 3, so that's just 0.1143. All right. Part D, the velocity of water flowing at, this almost looks like a velocity, but it's meters cubed. So this is a flow rate, cubic meters per second, so volume per second, through a fire hose nozzle. All right. And so this is a flow, so that's a Q. And we have a couple different formulas for Q, but this one has velocity in it and the size of the surface where the water is flowing through. So we're going to use the AV version of the Q equation. I can't think of it as a simpler one. We want V, so let's just rearrange this. So V is going to be Q divided by A. We're given Q, 0.019 cubic meters per second. And then to find A, it's just pi r squared. R is 1 centimeter, so 0.01 meters squared. Oh, come on. And so we got 0.019 divided by pi times 0.01 squared. All right, so we got Q is 60.48. And this will be meters per second since everything is good units. So we'll say 60.5 meters per second for the answer. 3 sig digs, good. All right, part E. Find the angular velocity of a, we need 0.5 meters, we need some units in here, wheel, in which a rock in the outer tread is moving 5 meters per second. So we're going to think of it, we're just worrying about the rotational motion, not the translational motion, but we're given a translational velocity. So let's just think about a wheel rotating. It's got a velocity on the outer edge of 5 meters per second. It's got a diameter, 0.5 meters, and so the radius is half of that, 0.25 meters. All right. And so we're just going to use our equation from up here again. So omega then is going to be V over R. And so that's 5 meters per second divided by 0.25 meters. And so omega 5 divided by 0.25, 20. radians per second. Okay. Part F, we've got torque on a lug nut of 10 torque. We want to find the torque that is on a lug nut when a 10 Newton force is applied at a 75-degree angle on a wrench, 75 centimeters long. So we got some sort of a nut here with a wrench on it, and we've got a force. It's not a perpendicular force, it's only got 75 degrees between the force, which is given as 10 newtons, and the moment arm, the length of the wrench, 0.75 meters, 0.75 meters. All right, so we have a couple versions of the torque equation, but this one is just using the basic force and moment arm. So torque equals RF sine theta. In this case, so theta is angle, this is R, this is F. So if we put these two end to end, right, theta is angle in between those, and that's, if you can kind of see, if you extend this and extend this, that's going to be the same angle, 75 degrees. All right, so theta is 75 degrees, so we just plug it right in, 0.75 times 10, 0.75 for R, 10 for F, sine of 75 degrees. All right, so we get 7.244 Newton meters for torque, since we've got everything in meters and newtons. Yes, that's good. So 3 sig dig 7.24 Newton meters. Good. All right. Part G. I guess I should be checking my answers to see if they agree with what I did previously, but I think we're doing all right. Nope, I screwed up here. So let's go back and fix this one. 4/3 pi r cubed. All right, so this is the wrong number. Sorry. Multiply by another 0.2. Let's do that one over. 1,000 times 9.81 times 4 times pi times, I don't know how to do cubes on this thing, but we can do 0.2 times 0.2 times 0.2, and then divide by 3. All right, still different than the answer I had before, but I guess we'll go with it. So this one is 328.7. 328.7. Let's do 329. 329 newtons. Okay. This one. Okay. I have a little bit different number, but I think I did it right there. Okay, let's go on to G. So part G, the angular acceleration of a flat disc frisbee, radius 10 centimeters, and mass of 0.25 kilograms. We got a disc, radius is 10 centimeters, so 0.1 meter. And we've got a torque, so we're just going to assume that there's a force that's causing a torque, a rotational torque on the thing of 5 Newton meters. So we're going to assume it's rotating around its center like frisbees do. All right, so we're going to use the torque equation here. Torque equals I alpha. So this is really Newton's second law, the net torque, the sum of all the torques equals moment of inertia times alpha, just like F equals ma, torque equals I alpha. In this case, we've only got one torque, which is the torque of the force on it for throwing it, so we'll just go with T equals I alpha. We want alpha, so alpha equals torque over inertia. We are given the torque is 5 we need to figure out what I is. All right, so I is inertia constant. We gave in class, I gave you a table of several different inertia constants for different shapes. So we got this axis of rotation through the center, and for a flat disk, I think it was called, it's just 1/2 mr squared. All right, so it'll be different for different shapes. So in this case, we're going to have 1/2, and the m is 0.25 kilograms, good unit, and then r is 0.1 meters squared. So let's plug all that in. 5 divided by 5 divided by 0.5, or 1/2 times 0.25 for the mass, and then 0.1 squared. Looks good. 4 times 10 to the third, so 4,000 radians per second squared. 4,000 radians per second squared. Okay. Next page. Okay, we have some numbers given at the top: viscosity of blood, density of blood, viscosity of water, density of water, and we're looking for on the first one. So these are all find the following. Find what? Find the mass of 0.055 meters cubed of water. So when we have cubic meters, that's telling us a volume, right? So we need an equation to relate volume and mass, and that sounds like density, right? So density equals mass per unit volume, right? Mass over volume. And so if we want mass, that's going to just multiply through by volume. It's going to be rho v. This is all talking about water, so rho of water, and the volume of water, which was given there. And so the density of water, 1,000 kilograms per meter cubed, times the volume of water, 0.055 meters cubed. So those cancel, and we're going to add up with kilograms. Just multiply by 1,000, so we're going to get 55 kilograms of water. Okay. Part B. Find the pressure difference needed to get a flow rate of blah through a 25 centimeter long artery, radius 3 millimeters. Okay, so this is giving us an L. Let's convert it to meters, 0.25 meters. This is giving us a radius. R is 3 millimeters, so 0.003 meters. What is this thing? It says it's a flow rate. So that means Q is equal to 7.89 10 to the negative 11 meters cubed per second. So again, it's a volume per second, so that's a flow. All right, so we're looking for a delta P. We've got Q, L, and R. We've got densities and viscosities. So we have the basic equation for flow is A times V, but we got more information here, right? So we need to go ahead, and we don't have any velocity. So let's use the more detailed equation. Find it so I don't quote it wrong. It's kind of a messy one, but we got pi r to the 4th delta pressure divided by 8 A to L. So viscosity on the bottom. All right, we want to find the pressure difference. So we've got Q, we've got R, we've got viscosity, we've got length. So we've got everything except for the pressure difference. So let's just rearrange this to solve for pressure difference. Delta P, multiply both sides by 8 A to L. So we got Q times 8 A to L divided by pi r to the 4th. That is an eta. Okay, and so This plug stuff in. 7.89, 10 to the negative 11. Good units, meter cube per second. 8 eta. This is talking about blood. Eta is viscosity of blood, so 2.084, 10 to the negative 3 Pascal seconds. Length, 0.25 meters. All right, divided by pi and r 0.003 to the 4th power. I really should learn how to do exponents on my calculator. All right, so let's plug this in. So we got 7.89 negative 3, no, not negative 3, negative 11 times 8 times 2.084 negative 3 times 0.25 for the length, and then divided by, let's get some parentheses, pi times r to the 4th, which is r squared times r squared. Let me do it that way. Just double check we got everything. Whoops. I did 0.03 instead of 0.003. Let me fix that. .0033 millimeters, not 3 centimeters. 7.89. Alright, looks good. So we end up with delta P. Doesn't look good. What did it do? Seems awful small. Let's just put some parentheses in just in case. But it looks okay. Maybe I just copied it wrong. 1.29 times 10 to the negative 3 pascals. We'll go with that. Very small number. 1.29 times 10 to the negative 3 pascals. But this is a very small artery, so I guess that's okay. That's the difference in pressure for ones. So it's very short and very small, so we'll go with that. Okay, part C. What is the Reynolds number for water flowing 0.2 meters per second through a 0.05 diameter pipe? And then, is this laminar flow, yes or no? So for laminar flow, that's what Reynolds number is about. Is, remember, for the Reynolds number, if it's less than 2,000, then we've got good laminar flow. If n sub r is greater than 3,000, then we have turbulent flow. So basically, we're just going to calculate the Reynolds number, look at the size, and decide if it's laminar or turbulent. So we've got 2 rho VR, velocity V, R over viscosity eta. All right, so we got 2. We're talking about water, so we got 1,000 kilograms per meter cubed, and we got velocity 0.2 meters per second. We got R 0.05 divided by 2 because that was diameter, and then divide by eta for water, viscosity of water, 1 times 10 to the negative 3 Pascal seconds. All right, so we plug all that in and get the Reynolds number. 2 times 1,000 times 0.2 times 0.025. We're cutting that in half, and then divide by 0.001. Equals 10,000. Alrighty. So the Reynolds number is 10,000. Is it laminar flow? Not less than 2,000, so no, not laminar flow. Alrighty. Part D, find the flow rate caused by a 1.5 kilopascal pressure difference across the 2 millimeter radius artery that is 40 centimeters long. Alright, so this one, again, we're looking at flow rate. Flow rate is Q. Q, we have the AV kind of equation, or we have the thing with the viscosity and the pressure and all that, and then it looks like, you know, we've got pressure and we don't have velocity, so we're going to go with the equation. That's the one with all the pieces. So we want Q, so we don't have to rearrange, so it's going to be Q is going to be pi times, I guess we should go ahead and write it, r to the 4th delta p over 8, that's an r, 8 eta L, pi, r is 0.002 to the 4th, delta p, 1.5 times 10 to the 3rd, pascals, right, kilopascals. 8 eta, we're talking blood again, so we're going to use the 2.084, 10 to the negative 3rd Pascal seconds, and L 0.40 meters. So this is L, this is R, this is delta P. Okay, I think we've got everything in good units. My calculator to cooperate here, so we're going to have pi times 0.002 squared times squared, just to get to the 4th power there, and then times 1.5 10 to the 3rd pascals, divide by, let's get some parentheses, 8 times 2.084 negative 3rd power times 0.4. Alright, 11.306.3031 10 to the negative 6. Okay, so Q 11.3 10 to the negative 6 cubic meters per second. Again, cubic meters are huge things, so a very small flow number makes sense. And that's what I got last time I plugged it in too, so that looks good. Alright, keep on moving here. So now we've got 10 meter uniform density plank, fulcrum, 4 meters from one end, 20 kilogram mass on that same end, 10 kilogram mass on the other end. Person adds force 2 meters from the fulcrum on the 20 kilogram mass side. Alright, to balance the plank, assume positive is, so draw free body diagrams. And I just realized I did this problem wrong when I did it before, so we're gonna just do it here. So that's supposed to be 4, so so 10 meters altogether. We've got uniform density, so that means we're just going to assume it's all nice and even, and so the mg of the plank, m plank times g, the weight of the plank, will be right in the middle, right at 5 centimeters from each end, which is, 5 meters, and it'll be 1 meter from the fulcrum. All right, so we're going to be doing looking at rotations about the fulcrum most likely, and so we'll go ahead and calculate or give distances from the fulcrum to get our moment arm kind of stuff, because it's looking like a torque problem. All right, so I really shouldn't have this free body diagram here. I mean, let's call this a force. This is force of the fulcrum. Force of the fulcrum is this point, so this is the fulcrum point. All right, and then fulcrum is 4 meters from one end, and then the 20 kilogram mass is on that same end, so we're going to have M20 times G as a force on this end, and a 10 kilogram mass on the other end, so let's call it M10 times G to get the force. Force is mg for a weight. And then it says a person adds a force 2 meters from the fulcrum on the 20 kilogram mass side. So the person is going to add a force here, and let's just say, so this whole distance is 4, so we're going to have 2 meters here, whereas this whole distance is 4. All right, so then of course then this distance is 6. All right, and so this one is, we're going to call it force of P for force of the person. Alrighty, so I think we've got everything. We're going to say the positive torque is counterclockwise, just for completeness. We can go ahead and give our x and y directions. It's the normal x and y looks good here. Okay, so I'm going to wish I could see both sides probably. Part B, what is the torque about the fulcrum caused by the plank itself? All right, so the plank itself has this mg, mass of the plank times g, and since it's a uniform thing, we're going to say it's operating right at the center. And so remember, torque is force times moment arm times sine of theta. In this case, we've got the moment arms, this different distances along the plank, and all of the forces are straight up and down. So all of the angles are 90 degrees. We would say yay, hooray, so that we don't have to do any, anyway, all the thetas are 90, so all the sine thetas are 1. Right, so in this case, the torque of the plank is going to be RF sine theta. R is just 1, right, the distance from the pivot point to where the force is acting, so it's just 1 meter. So 1 meter, and the force is m plank times g, and theta is 90 degrees, so this whole thing is 1, so times 1. And so that's a 1. And so we've got m plank, 5 kilogram plank, we got the 1 meter, anyway, 1 meter, and then the g, 9.81 meters per second squared. And so we got torque of the plank, whoops, is just 5 times 9.81. 49.05 Newton meters, or 3 sig digs, 49.1 Newton meters. Okay. What torque must the person produce to balance the plank? All right, so we've got a little bit of a equation to write here. Hopefully I have enough room. So to balance the plank, so it tells us the thing is in equilibrium, and so we're going to have to add up all the torques, and then you do equal 0, right? Newton's second law in rotational form. So we're going to say that, so to balance, sum of the torques is going to be I alpha, but if it's balanced, alpha equals 0, so the sum of the torques equals 0. Right? So what torques do we have here? Let's just start adding them up. Start on this side, and so the first one on this side is the force is mg, and the moment arm is 4 meters, right? So for the 20 kilogram mass, and so we're going to have, let's just write it out, I guess, m20 times g times 4 meters, and let's get a sign. Is that making a counterclockwise or a clockwise torque? So here's a point, and it's here, so it's pushing around like this, so it's a counterclockwise, so it's going to be positive. Just put a little plus on there to remind us. All right, next torque is from the person, and the person is pushing. We're assuming, we don't really know what this force is. We're assuming he has to push down to balance the stuff on the other side, assuming this one isn't big enough. We could be wrong. We might get a negative sign, but let's just go with this. So we've got the force, we call it F sub P, and it's 2 meters from the end. So again, I should have put a sign. We'll just put a 1 there for the sine 90, right, being here. And again, this one is causing a counterclockwise torque, and so it's going to be positive. So plus the force of the person times 2 meters, and then a 1 for the sine 90 degrees. Let's just keep doing that so we can remember that. Don't forget that there's that sine 90 in there, that everything is 1 though. And then next torque. So let's look at this force of the fulcrum is operating on the pivot point, right? So I guess we can go ahead and include it, but we've got a force times the moment arm, F sub F, times the moment arm is 0, right? Because the distance to the pivot point is none because it's on the pivot point, so that torque is really just going to go away. Right? Going to the next one, we've got the mass of the plank itself, and it's 1 meter away from the fulcrum, but it's causing a torque clockwise, so it needs a negative sign on it. Right? So it's going to be negative mass of the plank times g times its moment arm of 1 meter, and then the sine 90 is also just 1. Okay? And then one more out here, way out there, 6 meters out, the 10 kilogram mass, again causing a clockwise torque, so m10 g times 6 meters, and then times 1 again. So all that has to add up to be 0. And I think we know everything except for F sub P, so we can solve for F sub P. Let's solve for 2F sub P first, just to make it a little more clear. So 2F sub P is just what this term is, and then let's bring everything else to the other side. So these will become positive. So we have MPG times 1 and plus 6 M10G, and then this one will be minus on the other side, minus 4 times M20G, and that's all of those. Okay, so then FP is going to be mass of the plank, so we can, let's just divide both sides by 2 here, so those will cancel out. So then FP is mass of the plank, which we already kind of calculated, TP up here. Anyway, we're doing it again. So 5, let's factor out the G's from everything. So we're going to have a bunch of stuff times 9.81 for G, all divided by 2. So the first thing times G is mass of the plank, 5 kilograms. Next one is 6 times mass of 10 plus 6 times 10 kilograms plus, minus 4 times 20 kilograms. All right, let's plug all that in. So 5 plus 6 times 10 minus 4 times 20. All of that in parentheses times 9.81 times our g, because they were all multiplied by g, and then divide all that by 2. We get force of the person, negative 73.575. So we did estimate wrong, the direction wrong. So force of the person is negative 73.6 newtons. That's not what I was asking for. Okay, what force is needed to produce this torque? That's the answer that goes down here, is the force. And it's negative, so that means we drew it and wrote the equations assuming it was down. And so we got a negative sign for doing down, so that means it's up. So the force of the person is 73.6 newtons up. Okay. Up here we still owe me a torque, so let's go ahead and go back to torque. Torque is RF sine theta. Remembering all the sine thetas are 1. The torque of the person, the moment arm of the person is 2. So it's 2 times this F, 2 times 73.575. Okay, so the torque is, let's just go ahead and leave it as a negative 147.2. Negative 147 Newton meters. Okay, which means it's clockwise. So this answer really goes up there. Okay, so sometimes on these free body diagrams we don't know the answer ahead of time. We pick a direction. If we get a negative sign, it just means we picked the wrong direction. It's going actually the other direction. Okay, number 4. Find the angular acceleration of a top when a force of 5 Newton is applied by a string wrapped around the top where its radius is 1 centimeter. The question mark, but anyway, the inertia of the top is this. Okay, angular acceleration, force, inertia. All right, so thinking about the equations, this is again a situation where we're talking about torque because we got a force on a radius causing something to turn. So we're going to use the torque equals I alpha equation. All right, and so we're looking for alpha. Alpha equals torque over inertia then. Torque, we aren't given torque, but we're given things that have to do with torque, right? Torque is RF sine theta. And we're given I, so we're good with I. We got R, we've got F. So this is the kind of situation here. We've got a string pulling here with an F, and we've got a radius of 1 centimeter, so 0.01 meters. And so that angle there will be 90 degrees again, our friend, 90 degrees. So sine theta is just going to be 1, because theta equals 90 degrees. And so we can get alpha then is R, 0.01 meters, F, 5 newtons, divided by I, 5 times 10 to the negative 4 kilogram meters squared. All right. All right, so 0.01 times 5 divided by 5 to the negative times 10 to the negative 4, 100. Radians per second squared. All right. Newtons are kilogram meters per second squared. Anyway, since we've got everything in the right units, we can be confident that we get the right units for alpha, the standard units. Okay, part B. Find the kinetic energy of a basketball spinning at 200 RPM. The inertia of the basketball here. We don't care about tops when we're doing basketball problems. Okay, so what is kinetic energy when it's spinning? So like somebody's spinning it on their finger, whatever, at 200 RPM. So kinetic energy for a rotating thing, right? So for a moving thing, we have 1/2 mv squared. Well, let's just write the full thing, and then we'll 1/2 mv squared plus 1/2 I omega squared. Right? And so it says it's just spinning. It's not moving in any direction. Doesn't have a linear velocity. And so some parts of it do, but the whole thing is not moving. So the kinetic energy is of the center. Center is not moving. It's sitting there and spinning. All right. So this one is going to be 0. The 1/2 mv squared part is 0. So we just need to calculate the 1/2 I omega part. All right. We're given I. So that's easy. And so we just need omega. We're given 2,000 RPM, so that's a revolutions kind of thing, a rotating velocity, but we need it in radians per second. So omega is 200 revolutions per minute, but we want radians per second, so we're going to do 1 revolution to cancel those out. Is how many radians? 2 pi radians. And we want per second, so we're going to say 1 minute, 60 seconds, so the minutes go away. So now we got radians per second. So omega is 200 times 2 times pi divided by 60. .94 radians per second. Okay, so kinetic energy is 1/2 I 0.0503 kilogram meter squareds times 20.94 radians per second squared. All right, so we get 11.0 joules for the kinetic energy. Okay, another kinetic energy. Kinetic energy of a bowling ball rolling 4 meters per second with a radius of 10 centimeters. All right, so now this one it's rolling, so it's got translational velocity, and it's even given. This is v, and we're given the radius is 0.1 meter. We got m, 5 kilograms. All right, so kinetic energy, 1/2 m v squared plus 1/2 I omega squared. We can find things that we're missing. We are missing I and we're missing omega, but omega is related to v, I is related to mass and radius, so let's go with I first. So I for a sphere is 2/5 mr squared, whichever r. So it's 2/5. Our m is 5 kilograms, and r is 0.1 meters. So our inertia is, well, the 5's cancel. 2 times 0.1 squared. Okay. Let me pause this.